if you can't explain it simply, you don't understand it well. Recently, I've been studying for my data structures and algorithms class, and I understand nothing. So this is a last-ditch effort. I have 2 weeks to learn everything and even less to make this video. Can I, in the span of a couple of days, construct clear explanations of these highly abstract concepts that actually make sense? Or will I completely bomb my final? We're gonna find out together. Oh, okay, maybe it isn't that serious. Alright, before we get into the actual sorting, we need to talk about time complexity, also called big O notation, which apparently every CS professor is contractually obligated to be obsessed with. And look, I get it. Time complexity measures how your algorithm scales when you give it more data. It's basically asking, okay, cool, your code works for 10 items, but what happens when I give you 10,000? Here's the tier list and what you need to know to get through this video. O of 1, this is called constant time. Doesn't matter if you have 10 items or 10 million. It takes the same time. This is like checking if your backpack is empty. You just look. That's it, S tier. Then you have O of n, linear time. You double the input, the time doubles. Perfectly reasonable. This is like reading through a list once, like a normal person would. Solid A tier. Now we get into the big ones. O of n squared. This is called quadratic time. Double your input and your runtime quadruples. This is what happens when you compare every element with every other element. For small inputs, fine, whatever. For large inputs, your computer starts questioning its life choices. This is a C tier at best. Now we get to the sweet spot for these sorting algorithms, okay? O of n log n. This is where smart algorithms live. It's faster than quadratic, but not as unrealistic as constant or linear for sorting. It's the, nerdy try-hard school kid of time complexity. Easy A tier. So that's the framework. Now let's see how these actually play out with real sorting algorithms, because spoiler alert, some of these are going to be in that C tier. Bubble sort. This is the algorithm your mom points at outside of Walmart saying, hey, this is why you should go to school. And she'd be right, but let's talk about why it exists. See, computers don't have intuition. When you look at this array, you instantly know it's a mess. The computer, it just sees 4 boxes with numbers. It has no concept of sorted until we tell it, step by step, how to figure that out. So here's Bubble Sort's galaxy brain strategy, alright? You look at the first 2 elements. If they're out of order, swap them. Move to the next pair, keep going until you reach the end, and then repeat this entire process for the whole array. After one full pass, the biggest element has bubbled to the end. Cool. Now you do the whole thing again for the remaining elements, and you've got a sorted array. It's like if you tried to organize books by height, but you could only look at 2 books at a time, and every time you wanted to make progress, you had to start over from the beginning. Technically, it works. Practically, it's a bit of a pain. Here's the thing. Bubble sort makes roughly n-squared comparisons. So for 10 elements, that's about 100 operations, which is not bad for modern computers. But then bump that up slightly, say for 100 elements, you get 10,000 operations. This scales horribly, which is why nobody actually uses this in real life unless they're teaching a CS class. The complexity for this algorithm, at the best case, is O of n, if you add a check to exit early when it's sorted, but the average to worst case is O of n squared. So we've established that bubble sort is not great. Can we do better while keeping things simple? Yeah, we got insertion sort now. This is how the algorithm works. Insertion sort is basically how you'd organize a hand of playing cards. You pick up the next card, you compare it to the cards already in your hand, you slide it backward until it's in the right spot, and then you repeat until you've picked up all the cards. The key difference from bubble sort, you're maintaining a sorted section. If you notice, the left side of your cards or your array is always in order, and you're inserting new elements into their correct position every single time. This is way more efficient because you're not scanning the entire array every single time. You stop as soon as you find where the element belongs. But here's a catch. It's better, yes, if your data is almost sorted, like, maybe a couple of elements are out of place, insertion sort is going to absolutely fly through it. So while it is still O of n squared in the worst case because you can scan through the array about n squared times because maybe it's in reverse order, in practice, it's usually faster than bubble sort, which is a low bar, but hey, we're making progress. Okay, so for complexity, we have best case O of n when the array is neatly sorted, and for the average worst, we have O of n squared again. Verdict: legitimately useful for small datasets or nearly sorted data. Still quadratic though, which means we can do better. Alright, now we get into the actual smart algorithms. The ones that make you go, oh, okay, I see why people get paid to do this. Merge sort uses what's called a divide and conquer strategy, which admittedly sounds dramatic, but it's actually a pretty elegant idea. Here's how it goes. Divide. You split your array in half, keep splitting those halves until you have individual elements, and then conquer. Merge those pairs of elements back together in sorted order. You keep merging until you've rebuilt the entire array, now sorted. Think of it like organizing a massive library. Instead of one person trying to sort everything, you have multiple people each sort small sections. Then you combine those sorted sections together, which is way easier because they're already in order. Since both lists are already sorted, you only look at the front of each list. No scanning backward, no chaos. Okay, so complexity. Best, average, worst, this time is just OFN log n, but here's a catch. It does have good time complexity, but you have to compromise on space. It takes OFN space because you need that extra memory buffer for the merging. Okay, verdict. This is legitimately good. It's consistently fast no matter what input you give it. The only downside is memory usage. You need extra space for those temporary arrays. And now, the fan favorite, quicksort. Quicksort is the algorithm that somehow manages to be both elegant and slightly unhinged at the same time. It's fast, it's efficient, and it has just enough chaos energy to keep things interesting. Here's how it works. Pick an element as your pivot, usually the last element, but we do have a randomized quicksort as well. You partition the array, which means you rearrange everything so that smaller elements are on the left of the pivot and larger elements are on the right of the pivot. Your pivot is now in its final sorted, correct position. You recursively do the same thing to the left and the right sections. It's kind of like organizing a tournament bracket. You pick a reference point, split everyone into would beat the reference and would lose to the reference, then you repeat for each group. Eventually, everyone ends up ranked correctly. When quicksort picks good pivots, ones that split the array roughly in half, you get O of n log n performance. Each level processes n elements, and there are log n levels. In practice, quicksort is usually the fastest sorting algorithm. It's also in place, which means it doesn't need extra memory like merge sort, and it plays nicely with how computer memory works. But there's a catch, because there's always one. If you consistently pick bad pivots, like always choosing smallest or largest element, quicksort degenerates into OFN squared. This usually happens on already sorted arrays if you naively pick the first or last element as your pivot every time. Which is why, as I mentioned earlier, modern implementations use tricks like median of 3 or just randomize the pivot entirely. Okay, so the complexity for this is on best case or average case, we have OFN log n. Worst case, we have OFN squared because of terrible pivot selection. Alright, the verdict for this is that this is quite literally the industry standard. Most programming languages use this under the hood for their sorting functions. It's fast, it's efficient, and with good pivot selection, it's hard to beat. The real takeaway here isn't just memorizing which one is faster. It's understanding why these time complexities happen and how the approach you take completely changes how your code scales. As for whether I actually understand this well enough to pass my exam, we're gonna find out real soon. Wish me luck. Also, let me quickly interrupt here. Last video, 99% of people didn't subscribe after watching the video. I just wanted to tell you to subscribe and like, alright? Bye.